Okay. So now I'm going to talk about disaccharides and polysaccharides. So this is really just an extension of what we've talked about before. Now this, I'm going to go into some detail, and I'm going to show some examples, but really, this will be problematic if you don't understand Haworth projections pretty well and you don't understand the reactions pretty well. So if this is kind of not making sense, go back and look at a couple of the other lessons on particularly Haworth projections and reactions. So glycoside formation, the last reaction I talked about was where we have a hemiacetal, right? So we have a monosaccharide with a hemiacetal on it, and this could be alpha or beta, it doesn't matter, I can show it either way. What happens is we take an OH and we add R and we have an acid catalyst, and what we get is we end up getting R being attached here and then water. So this is a condensation reaction, right? But in this case, in the case of forming polysaccharides, or disaccharides and polysaccharides, imagine if R, so let me draw it down here. So I've got my, so imagine if we have our, so we'll have our OH here, and this is the alpha configuration. Again, I'm just picking at random, so I just decided that this was alpha. So I'm going to have my R group here, like this. But imagine now that my R group is another monosaccharide. It can be whatever we want, right? So I just have another monosaccharide. And what happens is I have the reaction happen, and it's still a condensation reaction. And what I get is I get this, and I get plus water, H2O. So in this way, we make a disaccharide. So it's two monosaccharide units connected together by a glycosidic linkage. So one functions as the hemiacetal, the other is an alcohol. Here's a little bit better drawing of the same. Now, it's very similar to the one I just drew in the background here. So let me get it back. The only real difference is the one I started with, this was beta, because I felt like. And this is alpha. See? So the glycosidic linkage is the bond in a disaccharide. It's the thing that this is the glycosidic linkage. It connects the hemiacetal carbon of one monosaccharide to just one hydroxyl group on the other. Now, yes, we could have attached to a lot of different places. I mean, there's a lot of different OH groups on here that could be possible sites for, oh man, that got messy, that could be possible sites for making these glycosidic linkages. So there are a number of disaccharides that exist, and I'm just going to go over a few examples. I'm not going to expect you to memorize these. I told you I did expect you to memorize, say, the Fisher projections of, say, fructose and glucose, galactose, and some of those. But let me show you what's important here. So maltose is called malt sugar. What's really important here is that, so here's a linkage. This is actually the same one I showed you before. But we have a way to identify and label the linkages. So the way the linkage is described is first I have, not always do I have an alpha or a beta, but in this case I do have an alpha or a beta. The alpha or beta is involved if the hemiacetal carbon on the first, well, and it has to be, otherwise we have to go through different means. It's not really a glycosidic linkage of the hemiacetal carbon. But the hemiacetal carbon here has to be involved. And this hemiacetal carbon, because it wasn't in the open chain form, it wasn't chiral, but it is chiral in the closed ring form, this first monosaccharide could be alpha or beta. This what this letter is describing, it's describing whether the first monosaccharide in the disaccharide is alpha or beta. So you see here, these are opposite each other, so this is alpha. That's why this is an alpha linkage. So we're not worrying about what's going on over here. That is not where the alpha comes in. The alpha is describing the linkage part. So we're looking here. So because those two are opposite, it's alpha. Now, the numbers come in. They're simply describing which carbons are involved. So if we number them 1, 2, 3, 4, 5, and 6, then we have 1, 2, 3, 4, 5, and 6. So unit 1, carbon 1 is involved, and it is attached to, and when we go over here, we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. The linkage connects carbons 1 and 4. 1 on the first monosaccharide, 4 on the other, hence the arrow in between. So the alpha describes the orientation of that glycosidic oxygen, and then the numbers describe which two carbons are involved. So maltose is defined. There's I'm going to show you a number of disaccharides, and there's basically 3 pieces of information that make up the identity of each of these disaccharides. The first is, what is the first monosaccharide? And in this case, it's D-glucose. And the second one is, what is the second disaccharide? Well, in this case, it's also, or second monosaccharide. In this case, it's also D-glucose. And then what is the linkage? Alpha 1,4. So what maltose is, it's 2 D-glucose units with an alpha 1,4 linkage. That is the identity of maltose. Let's look at another one. I'll come back to this. So cellobiose is also 2 D-glucose monosaccharides units, but it's different. It's different because the linkage is different. So this is why maltose is maltose and cellobiose is cellobiose. They're both 2 glucose units, but cellobiose is a beta 1,4 linkage, right? So that orientation is different. Now, let's go back up here and look at maltose. In all these cases, because this carbon that I've circled in each of these 3 is now an acetal. It can't open up anymore. It's not in equilibrium. It's stuck. It cannot toggle around between alpha and beta anymore. It's stuck in its alpha configuration. So it has to just stay like that. And if it could change, then the identity of maltose would change. So this is alpha maltose. However, this open one can still open, right? So it's still in equilibrium. So maltose, every single molecule of maltose, every single disaccharide must have this alpha linkage. But to describe maltose, a given maltose disaccharide, as being alpha or beta, we're not talking about this first one because it's alpha. There's no reason to indicate that. Maltose has an alpha 1,4 linkage, so there's no reason to indicate that. What we're talking about is the last disaccharide, right? Or the last monosaccharide, right? So this is alpha. So this is alpha maltose. This is beta. So that's beta maltose. This is the open chain form of maltose. So the second sugar, the second monosaccharide, describes whether that disaccharide is alpha or beta. The first one is the identity of the linkage. So let's look at another one. So you could have alpha or beta. So I just left this ambiguous, but you could have alpha or beta cellobiose. And there's, in truth, if you have a solution of cellobiose, it's in equilibrium. Lactose is a 1 beta D-galactose, or a D-galactose unit and a D-glucose unit. And it's take a look at this, identify what kind of linkage it is. This is carbon 1, this is carbon 4, so it's 1,4, and it's beta 1,4. This is not beta 1,4, I did that wrong, sorry. No, I had it right the first time, beta 1,4, going crazy, I guess. So it's beta 1,4, and this is different from cellobiose because the identities of the monosaccharides are different, right? So this is, the second one is still glucose, but this first one is D-galactose. And really, the difference is simply this one. The difference between celebiose and lactose is only that one chiral center. But it makes all the difference. Our bodies are chiral, so it matters. The chirality of every part of these matters in how we interact with it. In fact, our bodies can break down some linkages and not others. So our bodies are capable of breaking down maybe beta 1,4 but not alpha 1,4. It totally depends. And so the chirality of every part of this matters, which is why we're so meticulous about it. I should also point out that because we have this alpha beta form and this possibility of an open chain because of the hemiacetal carbon in lactose and celebiose and in maltose, we have this ability. These are all reducing sugars. Remember, a reducing sugar has the hemiacetal carbon. It has the ability to open. The one disaccharide that we're going to talk about that is not a reducing sugar is sucrose, table sugar. In its intact form, it's not a reducing sugar because the linkage, and also this is a big clue, the linkage is alpha, beta, 1, 2. So we list the one on top first. This is 1, 2, right? Why is this carbon 2 down here? Well, it's because it's a ketose. Because sucrose is a D-glucose unit up here, that's D-glucose, and then D-fructose, which is a ketose. Remember, D-fructose looks like this. Uh-oh. Okay, so it looks like this. So what we get is this is carbon 1, 2, 3, 4, 5, 6. So this is carbon 1, 2, right? So this is connected from 1 to 2. The first one, the 1, is alpha, but the second one is beta, right? So it's alpha, beta, 1, 2 linkage. And what's also really important is that this is an acetal, not a hemiacetal, because it goes OR, OR. This is also an acetal, not a hemiacetal. And because of that, there's no possibility of the open chain form. There are no alpha and beta forms of sucrose. There's just sucrose. And it's not a reducing sugar. It doesn't have that hemiacetal form. It's not a reducing sugar. It won't react to Tollens or Benedict solutions. And so we consider it not a reducing sugar. Polysaccharides are just taking this another step. Right? So I'll show you cellulose. Cellulose is it's a linear D-glucose polymer with beta 1,4 linkages, just on and on and on and on. It's just carrying this disaccharide idea out. Now, cellulose is not a reducing sugar either. And this is because even though the last one in the chain may be, or the last one in the chain does have a hemiacetal carbon on it, the fact of the matter is you have hundreds or thousands or tens of thousands of these monomers all stacked in a line. And the one, having just one molecule of something react isn't necessarily going to be visible to us. So having just one lonely little hemiacetal on the end of a 1,000-chain polymer isn't really going to be detectable when we react it with Benedicts or Tollens. It does react, but it just isn't going to react. There isn't going to be enough of those. So they're not reducing sugars either. Here's another one that's starch. And really, I just want you to get the idea of what they are. So I'm not going to spend too much time on polymers. I just want you to understand it's just the same idea extended out and out and out.